Chapter 15, Weather Systems. In this chapter, we'll talk about the weather around us, the science of weather, from folklore to forecasting, air masses, mid-latitude cyclones and frontal systems, severe weather, thunderstorms and tornadoes, and severe weather, hurricanes. Weather, which is the state of the atmosphere at a specific time and place, can affect how much energy is received or lost, and therefore the temperature. Clouds will result in less solar radiation. Winds move warm and cold masses around, and storms can produce cooler air. Meteorology is the study of the atmosphere and its weather. Mankind has been trying to make sense of the weather since ancient times. In 1637, Descartes published first scientific text on weather, but he had no tools to make measurements. By the 1700s, the technology caught up. In 1643, the first barometer was invented. Gabriel Fahrenheit in 1714 and Anders Celsius in 1742 invented the first mercury thermometers. The hygrometer, which is an instrument that measures humidity, was invented a few decades later. A paradigm shift in our understanding of weather occurred. With the development of communications devices, information on weather from multiple sources became available, and patterns in weather data began to emerge. Weather systems always migrate from the west to the east across the United States. Fair skies are associated with high pressure. Rain often accompanies low pressure systems. And the U.S. National Weather Service was established in 1870. By 1872, it was creating national weather maps. By 1878, daily observations were being collected at hundreds of sites and relayed across the country by telegraph. Not until the early 1900s did Norwegian scientists identify the concepts of air masses and frontal systems. Air masses are large volumes of air with similar temperature and pressure. I think of them like a big blob. The frontal systems are locations where the air masses interact. In other words, the edges of an air mass. Few gas molecules exist there. These concepts allowed meteorologists to use raw temperature and pressure data to predict weather over large regions. The recognition of these basic types of air masses and their motions made it possible to develop rules for the evolution of weather systems. Later, these rules were turned into mathematical equations that could be programmed into computers to produce forecasts. Today, all weather information and data come from the National Weather Service. The NWS processes over 1 million surface, air, and satellite weather observations every day. There are 2 GEOs, which is geostationary operational environmental satellites, in orbit that provide weather coverage for 60% of the planet's surface. There are over 150 Doppler radar sites nationwide that are used to track changes in regional storms. A Doppler can detect dangerous swirling winds. An air mass, first of all, is a large region of the lower troposphere that has relatively uniform temperature and moisture content. The nature of the air mass depends on the source area where it forms and the changes that occur as it travels. Air masses are identified by their temperature and the moisture characteristics of the underlying surface. There are polar air masses that are found at the higher latitudes. There are air masses that are found near the equator, and they're called tropical air masses. They're formed in the warmer areas around the equator. There are maritime air masses that develop above oceans, and those are wetter. They have a lot more humidity within them. And there are dry air masses that form over the continents, and those are called continental. It either forms over land or it forms over water. If it forms over water, it's called maritime, and that would be represented with an M. Maritime polar would be moist and cold. And maritime tropical would be moist and warm. So a CA would form over permanent snow or sea ice. It'd be extremely cold, dry air that may move southward. A continental polar would form over the northernmost portions of North America, Europe, and Asia. It'd be cold and dry, but not as cold as the CA masses, the continental Arctic. Continental tropical would form over the continental interiors over land. It would be hot, dry air that is modified as it moves east or north. Maritime polar would form in the North Atlantic and Pacific and Southern Oceans. It would be cool, moist air that affects the Northeast and Northwest states in the United States. It's warmer than the continental polar air. It would bring rain to the coasts of Washington State, Oregon, and snows to the inland mountains. Maritime polar would move inland from the tropical Pacific Ocean, the Gulf of Mexico, and tropical Atlantic Ocean. It would be hot and humid. This would bring hot, humid summers to the southeast states. Air masses of North America. The circles show the source areas and the arrows show where the air mass moves after it forms. The source areas and the paths can influence weather patterns across North America. Air masses can gain or lose heat and or moisture as they move from one location to another. Air masses are principally modified by temperatures of the underlying surface and the topography of the underlying surface. Example, air heated by warmer land surface will begin to rise. It is unstable and will rise until the temperature matches the surrounding atmosphere. Air that is forced up over topography will cool and moisture will condense. The condensation removes moisture, leaving the dry air, the rain shadow effect. Here are the Cascade Mountains, and down here are the Sierras. When moist air comes in from the ocean over the continent, it hits the mountain, it's forced upward. The higher you go, remember, in the atmosphere, the cooler it gets. So it cools off. The humidity condenses into water droplets, and it drops the water droplets onto the mountains. And if it's winter, it's usually in the form of snow. Since that air mass has dropped its moisture over the mountains, on the other side of the mountains, it's usually drier. So look down here in California. It's wetter on the west side than it is on the east side of the mountains. If you were in Glacier National Park, that would be extremely evident with the Rocky Mountains. This side of the park has lush green vegetation, And on the east side, it's desert. That's called the rain shadow effect. The lake effect is common in states south and east downwind of the Great Lakes. Dry continental polar air masses pick up moisture as they cross the warm waters of the lakes. When the air mass arrives at the southern lakeshore, it cools, it saturates, and it precipitates. So when you hear, oh, we've got lake effect snow coming in, look out. It's going to snow a ton. Here's a satellite photograph of the lake effect. Here's Lake Superior, and the air mass is moving in this direction. Notice it's picking up moisture and it's condensing over the lake, and it's dropping it onto the land. Mid-latitude cyclones and regional scale low-pressure systems form between 30 degrees and 60 degrees north or south. I personally live at 34 degrees north. This is where continental polar air masses would form at my location. If I were in the ocean, it would be called maritime. This is where the continental polar and maritime tropical air masses collide in my area to form frontal systems. This collision zone migrates toward the south during the winter and toward the north in the summer. These air masses, or cyclone systems, the low-pressure systems, can be 1 to 2 kilometers across. It can affect much of the continent for up to a week. Mid-latitude systems tend to dominate weather patterns in the United States. Mid-latitude cyclones develop where surface irregularities, mountains, yes, I am at the foothills of the Appalachian Mountains, or water boundaries. This would cause a local sideways acting force to distort a front. The front is transformed as warm air pushes northward and cool air pushes south, generating a counterclockwise rotation. Here's a drawing of this rotation. At the point where a low pressure system, here's a low pressure system, is located, this is a cyclone. See how it's moving in a counterclockwise direction? It interacts with neighboring high pressure systems. A mid-latitude cyclone has formed. It is centered around the low pressure system, and it's characterized by warm red and cold blue fronts. Cloud cover concentrates over the fronts and low pressure center. Down here, this is the classic comma-shaped cloud pattern, which is associated with the mid-latitude cyclones. Look at this weather map. Yes, red is associated with warm, blue is associated with colder air. What I want you to look at are these lines right here. This one has little half circles on it, and this one has triangles located on the line. These are the front lines. This one happens to be a cold front, and this particular cold front is actually moving southeast. I can tell because that's where the triangles are pointing. This front is a warm front. It's traveling north and east a little bit. I can tell because that's the side the half circles are located on. The boundary between one air mass and another is called the front. Frontal systems, pairs of relatively narrow long, slightly curved regions where the air masses interact. It's the leading edge of the air mass. Frontal systems bring clouds and precipitation and changes in moisture, temperature, pressure, and wind direction. When a warm and cold front merge, they form an occluded front. An occluded front means that there's been an air mass that is cut off from the surface of the Earth. These are weather patterns typically associated with a cyclone, a low pressure system, over the central United States. This is a low pressure system, and it's moving in a counterclockwise direction. Here's the warm front with the red half circles, and this is a cold front with the blue triangles. These little marks here actually show wind direction and wind speed. Cold fronts are represented by blue triangles, warm fronts by red semicircles. Both point in the direction of the air movement. Which direction is this frontal system moving? Well, it's moving from the west to the east. Warm maritime tropical air from the Gulf of Mexico lies between two of the fronts. Advancing cold fronts. Warm air is pushed upward and over the advancing cold air. The warm air is less dense and therefore lighter than the cold air. Cold fronts slope steeply. They're not really curved. They're pretty straight. The rising air undergoes rapid cooling and condensation in a narrow region above the cold front. The condensing water vapor fuels the formation of very tall cumulonimbus clouds that usually produce heavy but short-lived rains. Here's a drawing of an occluded front. A cold air mass overtakes a warm air mass, and a nimbostratus cloud generates precipitation along occluded fronts. Notice that this particular mass right up in here is cut off from the ground, thus the name occluded. Movement of both fronts in this direction. Thunderclouds, because of the cold air moving under the warm air. It hasn't caught up with this particular mass yet. It hasn't created the occluded front yet. Advancing warm fronts. Warm fronts slope gently. They're usually more rounded. The warm air does not rise as rapidly, and it moves more slowly. The associated rain may last longer with a cold front. Weather events are not as severe with a warm front. Warm fronts extend over a larger area than cold fronts usually do. Temperatures and humidity rise, and the winds change direction. There are 3 stages in mid-latitude cyclone development over the United States. Here, the cyclone forms. This is a stationary front. Stationary fronts are represented with the cold front on one side and the warm front on the other of the same line. It's not moving, thus it's called stationary. In this map, the cyclone reached the mature stage with a well-developed warm and cold fronts. The cyclone began to weaken in this drawing as warm and cold fronts merged to form an occluded front. Notice that this line has half circle, triangle, half circle, triangle. That's the occluded front right here. And then they're separated here. This is the warm front and this is the cold front. Severe weather, as defined by the National Weather Service, has one or more of the following elements: a tornado, damaging wind speeds of more than 58 miles per hour, penny-sized hail or larger. Only 10% of all 100,000 thunderstorms that form over the U.S. each year have these conditions. Most thunderstorms are around 16 miles across and last only minutes to a couple of hours. Here's the life cycle of a thunderstorm. Here it's building. This is the cumulus stage. Remember, a cumulus cloud is heaped up. And if you're lying on the grass, staring up the sky, you can actually watch these grow. And it will grow through the troposphere all the way up to the tropopause. When it gets up here, it can't grow anymore because here it's getting into the stratosphere. Weather doesn't really happen up in the stratosphere. So this has grown through the entire troposphere. This is the mature stage where it's going to start precipitating. It's got updrafts and it's got downdrafts. Updrafts bring water droplets upward where they can freeze, and they come down. And then if they get caught in another updraft, another layer freezes on it, and it comes down. And if it gets caught in another, yet another layer will freeze on this particular water droplet, and it is called hail. And it will precipitate hail if it keeps in this circular motion. And if you cut a hailstone open, you can see how many times it went through that particular cycle, updraft and downdraft, and it keeps freezing another layer on it as it goes upward. Lightning. Lightning joins two centers of an opposite charge associated with a thunderstorm. There's cloud to ground lightning, which are negative charges in a cloud that are connected to the positive charges on the ground. There's also cloud to cloud lightning, which is the opposite charges in one or more cloud connecting. Here's a drawing of the different charges. Generally, the upper levels have the positive charge and the mid levels have negative charges. And below that, there's a mixture. Thunderstorms can occur anywhere in the United States, but the most lightning occur in Florida because of the topography. Central or eastern portions of the United States, there are isolated afternoon thunderstorms in warm summer months when the moist air rises. They are typically brief and associated with a single large cloud called a cell. Warm land surfaces heat the overlying air, causing it to rise, condense, and create a thunderstorm. Tornadoes are narrow, funnel-shaped spirals of rapidly converging and rotating air that form in association with thunderstorms. The near-circular low-pressure systems that rotate counterclockwise in the northern hemisphere. Pressure gradient is way more intense for tornadoes. Tornadoes generate the strongest natural winds on Earth. While a tornado may be very short-lived, a hurricane can live for days or weeks. A tornado, it's more like minutes or hours. Tornadoes are ranked on the Fujita intensity scale, which places them in a category based on the destruction that they cause. An FO, or Fujita 0, would cause tree branches to break, or it might break a sign. This would be a wind speed of about 72 miles per hour. And it continues to increase, and the damage continues to increase with wind speed and gusts, all the way up to an F5. This would be an incredibly strong tornado where it could pick up an entire house and throw cars and other large missiles more than 100 meters. Steel reinforced buildings would be badly damaged in an F5. What happens is a team comes out to assess the damage and determine what level on the Fujita scale the tornado would be. The rule of thumb: the weak tornadoes can tear shingles off the roof of a house. A strong tornado can tear the whole roof off the house. And violent tornadoes can tear up the entire house. Characteristics of tornadoes are that the funnels are generally less than 2,000 feet wide. The average funnel velocities are 31 miles per hour with highs of about 125 miles an hour. The path of destruction is typically 3 to 16 miles. Some may stay on the ground for over an hour and travel over 62 miles. The tornadoes follow the path of their parent thunderstorm. Most travel east or northeast, as they are often associated with mid-latitude cyclone thunderstorms. If you compare tornadoes to hurricanes, tornadoes form over land. Tornadoes last a lot less time, and they travel with the thunderstorm over land. Thunderstorms and tornadoes: the rotating wind, a near horizontal axis, produces a rolling spiral of wind. The updraft: the spiral of winds is bent into an arch by an updraft, so it would be going up and then coming down. One of the mesocyclones becomes stronger than the other. The tornado stage: a downdraft from the storm forces part of the mesocyclone downward, causing the rotation to be stretched toward the ground, and it forms a tornado. Why do you think U.S. tornado fatalities have declined in the past 50 or so years? Scientists have actually studied thunderstorms and tornadoes over the last 50 years. There's better forecasting and warnings. We have better equipment these days. Tornadoes occur when thunderstorm activity is at an optimum across much of the nation. More common in the Gulf Coast and Southeast states in early spring, and then that migrates to the Great Plains in late spring. Tornado Alley: the United States is home to the majority of the world's tornadoes, averaging about 1,200 per year. Warmer colors indicate greater tornado activity, which is focused along the Gulf Coast. Hurricane Katrina was the worst natural disaster to strike the United States in the last century. Are we doomed to repeat history? Can a hurricane strike in the same place twice? More than 1,300 people died in Hurricane Katrina. An estimated $100 billion in damage in communities in Louisiana, Mississippi, and Alabama. Hurricanes Harvey, Irma, and Maria in the year 2017 have been added to the list of the costliest hurricanes in history. Much of the damage had long been predicted for Hurricane Katrina. A dozen major hurricanes had made landfall along coastal Louisiana in the last century. Government reports, scientific articles, and newspaper stories had all predicted what would happen if a major hurricane made landfall near New Orleans. Who should address the issue? Scientists are best equipped to determine the probability and destruction of a hurricane, but no funds or resources to do much about it. The government has power and funds for levees or evacuation plans, but they don't always understand the seriousness of the threat. This graphic shows the anatomy of a hurricane. It also shows the locations of continental United States hurricane strikes between 1950 and 2005. Most of them have occurred along the East Coast and the Gulf of Mexico. Stage 1. There's rising humid air that's forced aloft, and condensation produces an unorganized cumulonimbus clouds. There's no indication of the near circular hurricane-like pattern at this stage. Stage 2. The westerlies, meaning the global winds, drive the developing storm toward the United States and the Caribbean. Air is moved toward the center of a developing low-pressure system. The low-pressure system strengthens, becomes more organized, and forms a tropical depression, which is a spiraling wind pattern that develops as the Coriolis effect imparts a counterclockwise rotation. This continues over time over warm waters and causes the depression to strengthen into a named tropical storm. And the wind speeds at this point are about 118 kilometers per hour. In stage 3, additional evaporation of warm water ensures a tropical storm continues to strengthen to hurricane status. The condensation occurs in the saturated air to produce an expanding cloud mass. The latent heat of condensation fuels the rise of air within the storm. The heaviest precipitation and the highest winds occur over central part of the storm, up to 400 kilometers across. The warmer, less dense air at the storm's center increases the pressure gradient and wind speed. A well-developed spiral pattern is evident in the cloud mass for stage 3. Cross section through a hurricane. Here's the upper level winds. There's subsiding air in the eye. The air is rising in the eye, therefore there's low pressure. Air near the perimeter of the eye is drawn into the eye wall circulation. There's converging low-level air in the outer bands and rising air in the eye wall rotating around the eye. The origins of August hurricanes from 95 to 2004. See, very few are started over in the Gulf or the Caribbean. Most of them begin over by the Cape Verde Islands off the coast of Africa. The North Atlantic hurricane season is from June 1st through November 30th. Now, this does not mean that hurricanes cannot occur before June 1st or after November 30th. They can and have. Hurricanes only develop over warm water above 80 degrees Fahrenheit. And the water has to be deep enough, at least 200 feet, for the hurricane to develop. It also needs sufficient evaporation and condensation to foster large volumes of moisture to foster the growth of huge cloud masses. The warm surface waters move north from the equator in the summer in the northern hemisphere, creating optimal hurricane conditions. The development of Atlantic hurricanes that make landfall are as follows. 2 or 3 weeks prior to landfall, the cloud mass develops over the warm ocean water. The warm ocean water is the fuel for the hurricane. Most storms generated in East Atlantic take about 3 weeks to reach the coast of North America. Katrina developed in the West Atlantic near the Bahamas. Hurricanes begin to grow when their warm, humid air is forced aloft. The rising air cools and condenses to form cumulus clouds that will develop into cumulonimbus cells. Earth's rotation imparts a counterclockwise rotation to the storm in the northern hemisphere. This rotation is 0 at the equator. Therefore, the majority of hurricanes originate between 10 degrees and 20 degrees north or south of the equator. To maintain wind speed, inflow of air into developing low-pressure system must be matched by the outflow of air in the upper troposphere. 1 to 2 weeks prior to landfall, the tropical depression will develop. The winds will be between 23 to 39 miles per hour. After about 5 days, this develops into a tropical storm. The winds will be between 39 to 74 miles per hour. Finally, a hurricane will develop, and the winds will be at least 119 miles per hour. The air pressure is the lowest in the eye, where the warm air is rising. The lower the air pressure inside the hurricane, the faster the winds. Hurricanes will continue to grow in size and intensity as long as underlying water temperatures remains above 80 degrees Fahrenheit. Precipitation concentrates within about 125 miles on either side of the eye, releasing up to 20 billion tons of water per day. Please note the difference of the size of the hurricane, and also note the timing. A tornado, there's very little warning of when it will strike. A hurricane, you know for a week before that it's coming. 3 to 7 days before landfall, Atlantic hurricanes are driven west by the prevailing global winds at about 6 to 16 miles per hour. Florida and Texas experience more landfalls than any other state. Hurricanes may turn parallel to the east coast or pass south of Florida to strike the Gulf Coast or the Caribbean islands. 2 to 3 days before landfall, the likely landfall site is identified. Evacuation should be in full gear by now. And if it's more than a Category 1, people should leave. 1 to 2 days before landfall. Size and slow motion of hurricanes means their impact is drawn out for several days. The effects can reach the coast before the worst effects from the eye, meaning the outer bands of the hurricane hit the coast before the eye arrives. Measurements are made off the coast by buoys to gather information about the eye. There were waves over 100 feet high during Hurricane Katrina. The winds in the northeast quadrant blow onshore, piling up water in a storm surge. The surges cause about 90% of the damage in coastal areas. This can potentially reach inland areas up to 6 to 12 miles from shore. Katrina had water that reached heights of 30 feet above sea level in the northeast quadrant of the storm. The winds in the quadrant blow offshore. In the case of Katrina, winds in the northwest quadrant pushed water from Lake Pontchartrain, located northwest of the city, over levees into the city. Hurricanes can take days to make their way onshore. Hurricanes lose intensity over the land because of frictional drag and the loss of their moisture source. They lose their fuel. Damaging winds near the core have speeds similar to an F1 to F3 tornado. However, a hurricane can last for days, not just a few minutes like most tornadoes. A hurricane can have rain up to 24 inches in just a few days over inland regions. The water causes major erosion and damage from the flooding. The erosion from Hurricane Ivan eroded most of northern segment of the Chandeleur Islands in Louisiana. Look at the islands here. They're pretty much not there anymore. In a coastal marsh in Rhode Island. The dates indicate when the sands were deposited and can be interpreted to represent when major hurricanes struck Rhode Island.